So if we go back to our carbon dioxide global warming thing with the fossil fuel, we can write a balanced chemical equation for the combustion of fossil fuels. And that's going to give us the relationship between how much fossil fuel is burned and the amount of carbon dioxide that is released. Now, fossil fuels are not a single compound, right? They're a mixture of a whole bunch of compounds. And so we'll see as we do this calculation that we're making a series of approximations. And so our final answer is not going to be precise, but it's going to be a good estimate. So we're going to use octane as a representative fossil fuel. So octane has 8 carbons and enough hydrogens so that we've got 4 bonds for each carbon, so that ends up being C8H18. This is a component in gasoline. At room temperature, it's a liquid. When it burns, it combines with oxygen, which is a gas, and the products are CO2 and water. Heat is also generated, and so that's why these are both gases. Balancing the equation, we come up with these coefficients 2, 25, 16, and 18. Those numbers seem a little high, but that's what they are. The coefficients here should always be in the lowest whole number ratios. We got 2 and 25, and can't get any lower than that. So what this equation is telling us is that we make 16 CO2 molecules for every 2 molecules of octane. So if I burn 2 molecules of octane, I get 16 molecules of CO2. Everybody okay with that? What if I burn 2 dozen molecules? How many dozen molecules do I get? 16 dozen. Because 16 just means 12. If I burn 2 moles of this, 2 moles, how many moles of carbon dioxide do I get? 16. So I can interpret the coefficients in a balanced chemical equation as representing individual atoms and molecules, or as representing moles of molecules. The moles of molecules is more useful because a mole of something is a reasonable quantity. It's visible, right? So this is important. The coefficients specify the relative amounts in moles of each substance. We can't say that 2 grams of octane makes 16 grams of carbon dioxide, because this is describing the interaction between particles. The masses are not factored into that. So you've probably heard this word before, stoichiometry. That is the study of the numerical relationships between quantities of reactants and products in chemical reactions. And it's a very practical study. So the amount of every substance used and made, the reactants and products, is related to the amounts of all the other substances. The law of conservation of mass factors into this, and the idea of balancing equations by balancing atoms. You can't have more mass after the chemical reaction than what you started with. You also can't have less. All of those atoms still exist, and they have to be accounted for. So let's step away from atoms and molecules and talk about pizza, right? I'm hungry, sorry. So let's think about making pizza. The number of pizzas that you can make depends on how much ingredients you have, right? So let's think about a very simple recipe for pizza. We need 1 crust, 5 ounces of sauce, 2 cups of cheese. Put those together, we make 1 pizza, right? So we can express this recipe mathematically as ratios: 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. We can look at, we need 5 ounces of sauce to make 1 pizza. I need 2 cups of cheese for every crust to make a pizza, right? we can use those ratios to figure out, well, if I had 10 cups of cheese, how many pizzas could I make? How many pizzas could I make with 10 cups of cheese? Well, we're not specifying how many crusts. So what if we say we've got as many crusts as we want, as much sauce as we want, we've got 10 cups of cheese. How many pizzas can we make? 5. How'd you do that? Divided by 2, right? Because for every one pizza, you need 2 cups of cheese. If I have 10 cups of cheese, I can use those ratios to build a conversion factor. This is dimensional analysis. I want to know how many pizzas. So I've got cheese. I want to know how many pizzas. So I'm going to divide pizzas by cups of cheese. And I need the relationship between the number of pizza and the number of cups of cheese. I get that from this recipe or the balanced chemical equation. I need 2 cups of cheese for 1 pizza. It's a relationship. I get 1 pizza for every 2 cups of cheese that I use. Everybody okay with that? So the units, cups of cheese, cancel out. I've got 10 times 1 divided by 2, and that gives me 5 pizzas. Right? And you may think, well, I don't need to write it all out like that because I can just do that in my head. Well, sure you can. But when we talk about masses of oxygen and masses of octane, can you do that in your head? No. I could, with my calculator, do that in my head, but I would, on my mental blackboard, I would be writing it out like this. I would be seeing that. Stoichiometry is probably the biggest reason that you need to know dimensional analysis. Because if you understand dimensional analysis, that's all that stoichiometry is. You follow the pattern with the units and it all falls into place. So the coefficients in a balanced chemical reaction act as conversion factors in units of moles. And we can use those factors to relate any 2 reactants or products. So here we have that equation for the combustion of octane. Getting a series of text messages. I don't know why. Just keep popping up and distracting me. So 2 moles of octane react with 25 moles of oxygen and produce 16 moles of CO2 and 18 moles of water. I can take any 2 of these and make a ratio, right? 25 moles of oxygen to 18 moles of water. They are all related to each other. So this is saying if we burn 22 moles of octane, how many moles of CO2 form? So what I'm given is moles of C8H18. Save that one. And I'm trying to find moles of CO2. Dimensional analysis. What am I starting with? What's got the number? And what unit are they asking me about? The balanced chemical equation gives me the relationships between the moles of all the things in it. And so octane and CO2 are both in there, and so I can do this in one step. So I'm told I have 22 moles of C8H18. One arrow means 1 conversion factor. Moles of octane to moles of CO2. Moles of octane to moles of CO2. To make the units work out, I need to take this unit and divide by that. So those cancel out. I put the units in there so that those work out. That makes my life easier because the units tell me where to put the numbers now. I don't have to think about it. The ratio connecting moles of CO2 and moles of C8H18 is the coefficients in the balanced chemical equation. 2 moles of octane, 16 moles of CO2. So in front of moles of CO2, I put the coefficient 16, and in front of moles of C8H18, I put the coefficient that had in the chemical equation. Now I'm going to use my calculator for this one because I'm not good at multiplying 22 by 16. And just like when we did those long calculations, what you do is you take the first number, you multiply by the top, divide by the bottom, just continue as far as you need, press equals, and there's your answer. So 22 times 16 divided by 2, and my calculator is telling me 176. The unit would be moles of CO2. Any questions? Do I have the correct number of significant figures there? I do. My starting number had 3 significant figures. These values here are exact numbers because they ultimately come from numbers of molecules, numbers of particles. 2 of these molecules form 16 of those molecules. Those are objects that could be counted. It's an exact ratio. So this doesn't affect anything, so I should have 3 sig figs in my answer. Of course, we don't usually measure things in moles because we don't have a balance that'll tell you how many moles of CO2 you've got on there. So we measure things in grams. So what we just learned is this amount in moles to amount of something else in moles, the mole to mole conversion. In the previous chapter, we learned how to take the mass in grams and convert to moles, or to take the amount in moles and convert to grams. Right? It's the molar mass. We get those numbers from the periodic table and the chemical formula. Right? We learned how to make those as well. So we're just going to put these things together. So the general plan for stoichiometry is written out real pretty there, but basically it comes down to grams to moles to moles to grams. That's the starting point. We'll sometimes need to mix it up a little bit, but that's where you start. Grams to moles to moles to grams, grams to moles to moles to grams. And you know you're getting it when you wake up in the middle of the night and you're mumbling grams to moles to moles to grams. Right? Just get it in your head. So let's do a more real example. So according to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10 barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15 grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. So this is back to how much CO2 is being produced by human combustion of fossil fuels. Well, what do we have here? They're telling us an approximate number of barrels of petroleum, the equivalent of this many grams of gasoline. So those things are equal to each other. This problem has some extra stuff in it, and I'm trying to show you how to weed that out. So it says that many barrels of petroleum is equal to 3.7 times 10 to the 15 grams of gasoline. We're going to use the combustion of octane as the representative equation. So, Yeah, what does that mean? Well, it means that because we can't calculate all the different compounds that are present in gasoline, because gasolines vary, like octane ratings differ between premium and regular gasoline, right? One has more octane. So we don't have an exact chemical formula for gasoline. So we have to make an approximation. So we're going to pretend that all the gasoline was octane. So we're going to say, well, the gasoline, we're going to pretend it's octane for the purposes of doing this calculation. It's a good estimate. So that's telling me how many grams of octane I have. I like to use the balanced chemical equation to help me organize the numbers that are given to me. So octane is this guy right here. I'm going to write the mass I was given under that formula. 3.7 times 10 to the 15 grams of that. It's asking me to calculate the mass of CO2 emitted when that burns. So CO2 is over here. I want to know how many grams of that. So I'm going to put a question mark because that's what I'm trying to find. We don't care about the amount of water that was given off. We're assuming that there's enough oxygen for all of this to have burned. So we don't care about those other two things. So what's the general path for stoichiometry? Grams to moles to moles to grams. So that's what I'm going to start with. Grams to moles to moles to grams. Well, what chemical do I have a mass for? Octane, right? So I'm starting with grams of octane, and what am I trying to find the mass for? CO2. So I want to end up with grams of CO2. So I can convert grams of octane to moles of octane. And I can convert moles of octane to moles of CO2. Because for every 2 moles of octane, I make 16 moles of CO2. And I can convert moles of CO2 to grams of CO2 using the molar mass. Okay, so there's my path. It's easy now. I have 3 arrows, so I'm going to have 3 fractions. I'm starting with grams of octane. There's the number. So 3.7 times 10 to the 15 grams of C8H18 times and a line, times and a line, times and a line. Grams of C8H18 to moles of C8H18. I always leave enough room. Next is moles of CO2. And finally, grams of CO2. Grams to moles to grams. So this is grams of C8H18 down here. These units are going to cancel out. Moles of C8H18, those are going to cancel. And moles of CO2, those are going to cancel. It's that same pattern. All the units in place, and now I go looking for numbers. I like to start with the one in the middle because it's the easiest. The mole ratio comes from the balanced chemical equation. So I just look at the coefficients in front of these things. There's a 2 in front of C8H18. So I'm going to write 2 in front of moles of C2H18. There's a 16 in front of CO2, and so I write 16. Yes, I could simplify that to 8 over 1, but why? My calculator will take care of it. I'm just going to write it down like that. Now I need some molar masses. These were not handed to me, so I either need to look them up or calculate them. We're going to practice by calculating them. So I've got the chemical formula here, C8H18, and so there are 8 carbons. Each carbon is 12.01, and 18 hydrogens. Each of those is 1.008. So if I'm doing this in moles, I'm going to get an answer in grams. 8 times 12.01 plus 18 times 1.008. Calculator shows me 114.224. That's grams of C8H18 is equal to 1 mole of C8H18. Now, we often just stop at the 114.224, but this is what we are implying. This is the mass in grams of 1 mole of that compound. So here I have moles on top and grams on the bottom. So I'm just going to put the numbers with the units. 1 mole weighs 114.224 grams. Yeah, that's too many significant figures. Too many significant figures inside the calculation never hurt anybody. How many sig figs is my answer going to end up with? 2. Because my starting number had 2. These mole ratios are exact. My molar masses are going to have more than 2 sig figs. So I'm going to end up with 2, and the ones in here, I just want to make sure I have at least 2. So then I need the molar mass for CO2. Let's do that somewhere else. So that's carbon plus 2 oxygens. So that's 44.01. So 44.01 grams of CO2 is the mass of 1 mole of CO2. Any questions? There's my equation. I just need to multiply and divide as I go across. It's easy to mess up on your calculator, so it's always a good idea to do it twice and see if you get the same answer. 3.7 EE15 times 1 divided by 114.224 times 16 divided by 2 times 44.01 equals so we already decided this should have 2 significant figures, so there's my 2 significant figures. I'm going to write down the next 2 digits, and then this says E16, which means times 10 to the 16 grams of CO2. So rounding to the correct number of significant figures, (1.1 times 10 to the 16 grams of CO2. This only has 2 significant figures, but if we think of where we got this from, there were a lot of approximations and estimations, right? Do we know exactly how many barrels of gas were burned in 2013? No. It's so big, and I mean, we can look at how many were sold or how many were produced, but do we know how many of those were actually burned? Some of them were saved for later, right? There were some that were burned from the previous year, and so that's an estimate. Equating this to a certain amount of gasoline is also an estimate, and then equating this gasoline to octane is another estimate. And so we don't want to end up with a whole bunch of digits, which would imply that we know the mass of CO2 very, very precisely, because we don't. Any questions? So let's compare the results. Volcanoes or petroleum combustion? So this is what we just calculated. 1.1 times 10 to the 16th grams of CO2 in a year, our estimate. Volcanoes produce about 2 times 10 to the 14 grams of CO2 per year. Well, are those the same? Are they different? It's a little hard to tell because they're just such unreasonably huge numbers. What if we find out, I mean, this number's bigger. How many times bigger? 1.1 times 10 to the 16 grams divided by 2 times 10 to the 14 grams. So the estimate is that human combustion of petroleum products, fossil fuels, produces 55 times more CO2 than volcanoes. So that definitely makes us think that, yeah, it's something we're doing that's causing this increase in CO2. It says nothing about whether the CO2 increase is actually causing the increase in the temperature. Probably. That's one of those things that's hard to prove. Any questions? Let's do another stoichiometry problem. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, according to this reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? Well, this first bit up here, this is just, backstory to try to make it interesting. We don't need any of that. We need the chemical equation, and we need the question here, mass of HCl in grams, and this mass of MgOH2. So under MgOH2, I'm going to write 3.26 grams. And under HCl, I'm going to write question mark grams. I'm identifying what I'm starting with and what I'm ending with. So what's the path? Grams to moles to moles to grams. So I'm going to write it up here. Grams to moles to grams. Well, what am I starting with? Grams of what? Magnesium hydroxide. The thing I have the number for, right? So I'm starting with that. And I convert grams of magnesium hydroxide into moles of magnesium hydroxide. I need the molar mass. What am I trying to find? Grams of HCl, right? And I can convert moles of magnesium hydroxide into moles of HCl because I have a balanced chemical equation. 1 mole of this to 2 moles of that. And then from moles of HCl to grams of HCl, molar mass. So notice in this path I've got up here, the units are changing and the chemicals are changing. But I can only change one thing at a time. So I'm going from grams of magnesium hydroxide to moles of magnesium hydroxide. I'm keeping the compound the same. I'm changing the unit. In the middle, I'm keeping the unit the same and I'm changing the compound. At the end, I'm keeping the compound the same and I'm changing the unit. You can only change one thing at a time. So there's my path, and I'm going to write my equation. 3.26 grams of magnesium hydroxide. It is important to write the chemical formula because moles of magnesium hydroxide, moles of HCl are not the same thing, and it's so easy to get them mixed up. So I'm going to have 3 fractions here. I'm going to write the units as I go along so I have enough space. So I'm going from grams of magnesium hydroxide to moles of magnesium hydroxide. I can make my line a little longer. And then I'm going to moles of HCl. And at the end, I'm going to grams of HCl. These units are marching along on the tops of those fractions. Okay? I take this unit and bring it down here. I want that unit to cancel out. So those cancel. I take this unit and bring it down here. And those cancel. And these cancel. If you struggled with the units in Chapter 1, now is the time to figure them out, because stoichiometry is going to be with us for the rest of the semester, and you might as well figure it out right now. It'll make your life so much easier. So I got the units in place. I need numbers. Like I said, I like to do the one in the middle because I think it's easy. It's always nice to start with something easy, right? So the mole ratio comes from the balanced chemical equation. 1 mole of magnesium hydroxide and 2 moles of HCl. 2 moles of HCl to 1 mole of magnesium hydroxide. Then I need some molar masses. I have to calculate those. So for the magnesium hydroxide, magnesium is 24. 24.31. And then I have 2 OHs, so that's 2 oxygens and 2 hydrogens. .326. So 1 mole of magnesium hydroxide weighs 58.326 grams. And I need molar mass for HCl. So 1 mole of HCl weighs 36.458 grams. I'm not rounding those molar masses. It's better not to. And almost always what limits my number of significant figures is the number they gave me in the problem. So the number they gave me has 3 sig figs, and so that's how many my answer will have. 3.26 times 1 divided by 58.326 times 2 divided by 1 times 36.458 divided by 1 equals 4.07. There's my 3 sig figs. I'm going to write down 2 extras, 5.4, and this is going to be grams of HCl. And then I can round that to 4.08. Any questions? .08. I'm going to save this example for Thursday.